find f prime of t, right?
Yeah.
So let's find f prime of t. So you want f prime of a, sorry, f prime of a. So we're going to do the limit as when h goes to 0. Is that good?
Yeah.
Yeah, sure.
Yeah. That's what
H goes to 0 of f of a plus h minus what? F of a all over
h.
So this place is going to be a plus h to the fourth minus 5 a plus h minus what? A to the fourth minus what? Well, plus 5a, yeah, because you're subtracting the negative. All over what? All over h, yay! So what do you have to do at this point? What do you have to do?
You have to factor out a plus h.
Well, not factor. We're not factoring.
Well, distribute.
We're distributing. Factoring is the opposite of distributing. It's like saying adding instead of subtracting, so that's why.
Okay.
So we have to do this out. Well, it just sounds wrong.
Yeah.
It doesn't sound anything. A squared plus 2ah plus h squared times a squared plus 2ah plus h squared minus 5a minus 5h minus a to the fourth plus 5a. So what's the first thing that cancels? 5a's. Those cancel. That's nice. And this whole thing is over h. Nice. So what do we have to multiply out now? Yay! The top limit as h goes to 0, a to the fourth plus 2a cubed h plus a squared h squared plus 2a cubed h plus 4a squared h squared plus 2a h squared plus h squared a squared plus 2ah cubed plus h to the fourth. Okay, sure, great. We'll take that. Oops. A little bitty smaller. Move it over a little bit. Minus 5h minus a to the fourth all over h. Now what do we have to do? What manipulation do we have to do? Combine what? Combine what? Combine like terms, yeah. So first of all, we can cancel something. The a to the fourth cancels with the... That's really nice. So let's take a look at 2a cubed h. Are there any a cubed h's? Any other a cubed h's? So how many do we have? 4, yeah, 2 of them. 4 a cubed h's, yep. So we took care of that. What about a squared h squareds? A squared h squareds? Right there. So 1, 5, 6. 6a squared h squared, 2a h squared, 4a h squared. H cubed. Oh, that should be a cube, shouldn't it be? Should this be a cube right here? That should be a cube, right? So it's 2a h cubed, like that, plus h to the fourth minus what? 5h all over what? So what does this become? This becomes the limit as h goes to 0 of what? 4a cubed plus squared h plus 4a h squared plus h cubed minus 5. And as h goes to 0, what happens? What does this equal? 4a cubed minus what? Minus 5. That is absolutely correct. 4a cubed minus 5. So we now know that f prime of a is equal to 4a cubed minus 5. I just thought of this, and I don't really know what it's called. Like these extra terms, I don't really have a special name for them. That would be an interesting thing to study, like the extra terms that you generate in the limit that end up going poof. Just something to think about. But there you go, 4a. So what was the hardest part about this question?
That the large
Yeah,
string of
factoring.
There was no factoring.
Distributing.
Yeah, so the algebra was hard.
Yes.
So you need to actually be able to do the algebra. Yes.
I have a question.
Don't multiply it out until you absolutely have to. Squeeze theorem, right? Exactly. Very nice. Okay, so let's try this here. Sine of 1 over x. What is that always less than? What?
Always less than 1.
Always less than 1. What's it always greater than? Or equal? Sorry, equal to. Negative 1. So let's see what we can get from the squeeze theorem here. Let's try to get this. What can we multiply everything by?
squared.
Thank you. Negative x squared less than or equal to x squared sine of 1 over x less than or equal to what? X squared. And what's the limit as x goes to 0 of negative x squared? 0. And what's the limit as x goes to 0 of x squared? 0. So therefore, by the squeeze theorem, we know that the limit as x goes to 0 of x squared sine of 1 over x squared is what? 1 over x is what?
0.
We know that the limit is 0. But we also know that from this function, what else do we know? F of 0 is what?
0.
F of 0 is 0. So you know f of 0 is 0, and the limit is
0.
therefore what?
Is f.
What's the question asking on this? That's important. What's the determine whether f prime of 0 exists. Determine whether it exists. And how do you prove whether a limit exists? It's there. The limit exists, right?
Yeah.
Determine whether f prime exists. The limit exists and what?
And the point is there.
Really close to what we want. We're not quite there. We want to determine whether f prime of 0 exists. So let's actually write. If we wanted to find f prime of 0 using our limit laws, so f prime of 0 would be f of what? 0 plus. We'll do it this way. I'm sorry. I need to add something here. It's the limit as h goes to 0 of what? F of what?
F of
0 plus
h.
minus f of
0.
all over
H.
all over h. Well, f of 0 plus h is the same thing as
0.
f of 0. What is f of 0? What is f of 0?
0. F of.
Oh, sorry, this is f of h. I'm sorry. I just made a typo. This is f of h. What's f of 0? It tells us in the function. What is f of 0? 0. All over h. And what is f of h going to be? H squared sine what?
1 over h.
Yes, so let me actually go to the next line here. So we have the limit as h goes to 0 of h squared sine what? 1 over h all over what? All over h, yeah. What cancels? H cancels, and we're left with the limit as h goes to 0 of h sine what?
1 over h.
So this means that f prime of 0 is equal to this. That's what we've proven. F prime of 0 is this. So if we want to prove that this exists, we have to prove that this exists. And do we have a really straightforward method that's almost identical to what we just did? Yes. What is sine of 1 over h always less than or equal to? 1. What's it always greater than or equal to? So therefore, negative h is less than or equal to h sine of 1 over h, which is less than or equal to h. And we know that the limit as h goes to 0 of negative h is equal to the limit as h goes to 0 of h, which is equal to what? 0. So what has to be true? What has to be true, therefore?
H
The limit,
yeah.
the limit as
h approaches 0
of
h sine
yes
1 over h equals 0.
equals 0. Exactly. So did we prove it equals 0?
Yes.
So therefore, does the derivative exist?
Yes.
Yeah, what is the derivative going to be?
0.
Yeah. Yeah, you can prove existence by finding out what it is. So does it have to exist if we have a value for it?
Yes.
Yes, absolutely. So what did we do there? We actually just found the derivative. F prime of 0 is going to be the limit as h goes to 0 of what? F of 0 plus h minus
f of h.
f of 0 over
h.
h. Right. In this case, it's going to be the limit as h goes to 0 of f of h minus 0 all over
h.
exactly. Good. What is f of h in this case?
H sine 1 over h.
H sine what?
1 over h.
1 over h. And I got to put that limit in there. I don't want to lose that. All over what?
H.
And this is the limit as h goes to 0. What cancels?
The h's.
The h's cancel, and what are you left with?
Sine 1 over
The
h.
limit
Well,
as h goes to 0 of sine of
1 over h.
1 over h.
Mhm.
Let's pause and think about this for a second. If the function was not defined there, if it wasn't defined at 0, then yes, absolutely the derivative wouldn't exist. The function isn't defined there, so it's gonna be a different problem entirely. But the function is defined, and that's where the limit goes. Let's see if the limit of this function x sine 1 over x, right?
Yeah.
But the derivative, we need to find what happens around the origin here. Let's zoom in even further. What happens? Do you remember this? Does this ring any bells? We did this like a week ago.
I just don't remember what happens.
Yeah, look. Let's zoom in even further and see what happens.
What would the graph of be?
I can't even see the freaking axis.
You're never.
Madness.
Why is it doing that, everybody? Why is it doing that? Why is it doing that? This. How many times does this oscillate between, I don't know, -1 and 1?
Infinite.
Yes. Number of oscillations. Infinite. And what does it oscillate between?
-1.
Yes. So is it possible for this thing to actually have a limit?
No.
One limit. So no one limit. So f prime of 0 does not exist. Does that make sense, Fitz? The key element here, could we use the squeeze theorem on this thing?
No.
We can't sandwich this between anything. And then you have to look at the logic of the question. That doesn't necessarily mean doesn't exist, right? Like there might be other ways of proving limits exist, right? But like look at the function. What happens as you get closer to 0? It oscillates an infinite number of times. So can it approach one limit? No. It goes from -1 to 1. If the oscillations were getting infinitely small, maybe, right? But are these oscillations getting infinitely small?
No.
No. We've seen what happens when the oscillations do get infinitely small. We've seen this before, where it goes, right? And what were do you remember the sandwich functions there we had? We had things like x squared and negative x squared. We had like x squared, and that's a poor drawing, and
negative x squared.
negative x squared, right? So we sandwiched the oscillations between it, so it went to 0. But in this case, are the oscillations sandwiched between anything?
No.
No, they went from -1 to 1. No, nada. Okay, we'll do one. So this is the derivative of some function f at a, right? So this is equal to the limit as h goes to 0 of f of a plus h minus what? F of a all over what?
H.
H. So we already have an immediate correspondence. We have the h there, and we have the h there, right? So in this case, f of a has to be what? What does f of a have to be?
It has to be.
What does it correspond to? What does f of a correspond to?
Root.
No, not the operation. What number? What thing that's
16.
already... No.
Oh.
2. F of a is 2, right?
Dumb of me.
No, it's no. It's not. It's not at all. There's the negative sign. The negative sign is already there. So what does the f of a correspond to? The f of a corresponds to 2, correct? And then it asks you for what does f of a plus h correspond to? What does f of a plus h correspond to? Yes, the 4th root of 16 what? Yes, the 4th root of 16 plus h. So it gives you a strong hint as to what a should be. What do you guess a should be from this? It really looks like a should be 16. And what function is acting upon the 16 plus h? 4th root. What's the 4th root of 16? 2. So in this case, f of x is going to be the 4th root of x. And what's our a going to be? And a is going to be 16. So this is the derivative of the 4th root of x at what x value? 16. Cool?
Yes.
Excellent. Okay, please put everything away except the pen. A, which is functionally equivalent to what we're about to do, which is if we let a vary, our definition for derivative changes to the limit as x goes to 0 of f of x plus h minus f of x over h. So that is the derivative at what x value?
X.
At x, that's the x value x, exactly. So we're writing, all we're doing is changing a to x. That's all we're doing.
I love this
Changing it
is
from
just
a
the same
constant
stuff.
to a variable.
Is that nice? They're the same. The derivative of f at x, f prime of x is equal to y prime, which is the same thing as dy over dx, which is the same thing as df over dx, which is the same thing as d over dx of f of x. The rate of change with respect to x of f of x, but usually f of x is y, so y over blah, blah, you got it. Big D f of x, d sub x f of x. The ones you will see by far the most frequently, you will see this, you will see this, you will see this, and you will kind of see this. You generally won't see this, you generally won't see this or this. This will come up in multivariable because you'll be able to take lots of different derivatives at a given point. There's lots of different ones when you add in more variables. But in general, by far the most common will be these three right there. Those will be the most common by far. They are the same thing. They are the same thing. They are the same thing. Something is differentiable. A function is differentiable at a point if the derivative exists at that x value, and it's differentiable on the open interval if it is differentiable at every number inside the interval. So if I say an interval is differentiable, what does that mean about every x value in that interval?
It has to exist.
It has to exist. Does it necessarily mean you can find it easily? No. Does it necessarily mean you can find it even remotely easily? No. Finding derivatives can be straightforward. It can be very, 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 very difficult, if not impossible, for you. The one example you can think of always, the one that breaks a lot of the exceptions, is something like an absolute value function. The derivative, if this is your x equals a value right here, the derivative coming from the left, is that going to be positive or negative?
Well, it's going to be
Is this
positive.
positive?
The slope
Exactly.
is positive.
The slope is positive. But if I'm approaching from the left, what's the slope of this line right here?
Yeah,
It's negative, right? So therefore, is the derivative said to exist at x equals a?
No.
No. Is it continuous there?
Yes.
Yep.
Yeah, it is continuous there, but the derivative does not exist. So if it's differentiable, you get continuity. But if you have continuity, do you always get differentiability? No, it's an indicator. It might be okay, right? But does it guarantee it?
No.
No, it does not guarantee it at all. It does not guarantee it.